So, you are given a text and the pattern P, which is typically much less than n. You have the following kind of queries. Echo find whether P occurs in T, and here by this I mean as a substring, and you may be interested in number of occurrences of P. You may be interested in all positions, starting positions. Okay, so this is like a Boolean query. The answer is yes or no, and this is a number, how many occurrences, and here is a set of positions in the text where it's appearing, right. So, this is a classical problem, well studied, gained a lot of importance in the last several years thanks to search engines and computational biology, where one is interested in these kind of queries. And there are also variations where you want to allow certain kind of mismatches or allow some don't care symbols in the pattern in the text and so on. Okay. But we look at the simplest variation of these questions. So, the naive algorithm would be, so you have all of this over an alphabet, some finite alphabet. So, these characters are coming from this small alphabet. So, a naive algorithm would be to slide this window. So, take your pattern and maybe start matching with the text one by one until there is a mismatch, and when there is a mismatch, maybe then you start all over again and start from here, and when there is a mismatch, then you start learning comparing from here and so on. So, yeah, slide the pattern yep. Zoom in on the board. Okay. Is that okay? So, what would be the worst case running time? So you want to do this even if you find a match, particularly if you want to find all occurrences or number of occurrences, even if your whole thing matches, then you want to start all over again and start matching from the second character and so on. So, what would be the overall running time? Yeah. So, it is like m into n minus m, because yeah, the last thing you just go up to this point. So, it's if m is very, very small, then this is pretty much mn. Okay. So, is this algorithm clear? It is just if your text is and maybe I am looking for, then I start matching like this, and okay, sorry. So, I fail here, there is a mismatch, then I start looking at matching from here, and there is even here already there is a mismatch, and then I am going to start matching, there is a mismatch and so on. So, in the worst case, you may go all the way and your mismatch may happen at the mth match query, and then you start all over again. So, that is like an mn running time. n into n minus m.
Yeah, because this n is very large as compared to m. So if you are just doing this matching, so again you are doing this matching, again you are doing this matching, but sometimes this matching happening. So n goes
Okay.
to n, right?
So there is a question whether the running time is it really m times n minus m or n times n minus m.
Every time you are doing m comparison.
Right. Every time you are doing m comparisons, and how many times? It's n minus m times, right? How many times you slide the window? N minus m times, right? And every time in the worst case, you may do m comparisons. So it's m into n. Okay, so now, of course, there are better algorithms. So let's, I mean, hopefully you've learned this in your automata course. So suppose I want to, so let P be given in advance. Let's say fixed pattern, maybe then what is the question I am interested in? Okay, or and let's define this language L to be all strings in X contains P as a substring. Right. So all strings that contain AB, 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 AC, B as a substring. What do we know about this language? It's a regular language, right? It is a regular language. Hopefully you learned this in your theory of computing or discrete math or whatever course. So it's a regular language. So you can construct what is called a deterministic finite automaton, and for this language. So then the question boils down to, so then we can construct a deterministic finite automaton. Then this question, whether P occurs in T, boils down to what? So let yeah. So let exactly. So how do we? What is the phi tuple? How do you represent a DFA? That I know. Q sigma delta, and then your initial state, and let's say set of final state. Okay. Now what is this called? Is what I am saying.
This is an automated
Right. So let's call it M. Right. So this is a DFA, deterministic finite automaton accepting L, right? So this is a, we'll look at some examples. So this is a finite automaton which accepts all strings that contains X. So given that contains P, right? So now this question, does P occur in T, is the same as, okay, does T belong to that language in the context of automaton? Is it accepted by M, right? So therefore, does P occur in T is the same as is P accepted by this language, this machine. Okay. So this is one way to solve it. So take your pattern, construct the deterministic finite automaton, and then take your text and run it on the machine. Now actually it can answer all the questions on the automaton. We will see example where you run your text, and when you hit the final state, you know that it is accepted by your automaton. and so it is in the language. So your pattern is in the string, but you don't stop, you just continue with running through the text, and then you will see all possible occurrences. You can have a counter every time you reach your final state, then that's the number of occurrences. So you can solve all these questions by running your text on the machine, finite automaton, right. So now everything boils down to how do I construct this automaton, right. And how much time does it take, right? So let's look at it on an example, and then we'll learn how to construct this automaton. So let's take that pattern. Computing an NFA is very easy, right. So I start with state 0. Okay, what are these symbols? The Q is a set of states, sigma is your alphabet, delta is the transition function which tells you I am in a state and I get this symbol, where do I go? S is the starting state and F is the set of all final states. Okay. So everything is about delta, right. I am at a particular state. So I start, this is my starting state, right. Let us call this S, and when I get an A, then I found a match. So let me go to state number 1, and when I get to B, I go to state number 2, 3, so my sigma, let's say, is ABC. And this is my final state. Okay. This is start state, and this is the only final state. So AB, AB, A, C, B, right. And I can just write AB here, and that would be a not a DFA. It's a non-deterministic finite automaton. So I could just go and write, okay, non-deterministically, when I see an A, I go here, and when I see a B, I go here, and I could just put AB everywhere, right. I don't know when I jump to B, I just non-deterministically do that. Then that would be a non-deterministic finite automaton, but I want to construct a deterministic finite automaton. So let's see what I would do, right. Let's fill up this transition function here. So Q has 7 states because my pattern length is 7, right. M is 7. Okay. Yeah, so Q has 8 states, sure. Okay. So my Q is 0, 1, 2 up to 7, and my sigma is ABC, and S is 0 and F is 7. Now delta is defined. Delta is where all the work is, right. Let's figure out how do I compute delta. Okay. So for this pattern, if I get a B, what should I do here? Stay there, right. If I get a B, I just stay there because I haven't found any match. If I get a, I go here. What do I do here if I get an A? So if I get a B, I'm going to go there. If I get a, so if I get an A, you stay there. Now we'll right. We will figure out if I am in delta, I am in state number Q, and I see a sigma. Where do I go, right? Somehow here it looks like I stay there. Why? because I still have one match, right. As long as I keep saying A, I am seeing a match, right. We will formally define how to get this and compute it, right, but let us at least fill it up for this example. So, here if I get an A, I am going to go here. If I get a B, what should I do? I get a B, then so what is my state? I've got an A, B, B. So, the suggestion is to go back to 0, right, because I haven't found any match. A, B, B, if I get a B, I just go back to 0. If I get an A, I stay here, and if I get an A here, what should I do? At state number 3, I get an A. So, I got an A, B, A, A. So, you are telling me go back to 1, not really to 0. Do not say that you got a mismatch, so start all over again. No, you somehow got one match. So, go to state number 1. Okay. Now, what is it formally and how do I compute it? We will keep building your intuition on this. Let us see. So, now if I get a B, what should I do here? In state number 4, I get an A, I go here. If I get a B, I have got an A, B, A, B, B. So, I got an A, B, A, B, and now I am getting a B. So, I go to 0. If I get a B. Okay, and now if I am on 5, oh, I also have to fill up what happens if I say a C. I think I just go all the way back or something, except maybe here. Okay. So, now if I get an A, what should I do? In state 5, so I have got an A, B, A, B, A, A. So, A, B, A, B, then I got an A, now I am getting a at position 5. So, I should go to 1 because I have got one match, right, because the A is a match. So, I go to 1, and if I get a B here, four, right, yeah, because I actually got 4 matches now. A, B, A, B. So, I go to 4. This is great, right. Even though it is a mismatch, but I still managed to gather some amount of match. Okay. And so, you can just sort of fill it up. Now, if I am in 7, I mean I do not stop here, because if I really want to care about the Boolean question, does it appear at all, I can stop here, but if I want to compute all occurrences and count, then I just going to continue here, right. So, let us from 6, I am going to leave a gap here, but if I am at 7, which means I got A, B, A, B, A, C, B, now I get a. What do? I go to 1 because I got a match, right, one match. And if I get a B, go all the way to 0, right. Okay. So, this is how you build your automaton, and once I have the automaton, which is basically this transition function, then to compute all occurrences, what do? It's dead easy. I take my text and run it, right, run it on the DFA, start from state 0, and depending on what symbol I see, it tells me where to go, and I just keep following it up. Every time when I reach this state, then I know I count -7 and say that is one occurrence, starting position of one occurrence of the pattern, right. And if you want to know how many occurrences, you just have a counter and keep adding it, and you just follow through the symbols as long as you finish your text. So, how much time does that take? Let us just order n, right. after you construct the finite automaton. And how do I construct the finite automaton? I have to figure out what this is. If I am at a state q and I see a symbol, where do I go? I have to figure this out. After I do that, then I take my text, run it on the finite automaton, and that takes order n because that's the transition table is somewhere there. So, I just have to index, I am at this state and I get this symbol, where do I go? Just keep going, keep going, keep going, and then you can run through the whole text in order n, right. So, order n after DFA construction. Good. So, now let us see what is this. If I am at state q and I see a sigma, where do I go? Okay, yeah. So, you all told me that I am here, if I see a I should go to 1, and if I see a b, you go here, right. How, what is this, why, what? Okay. So, yeah, state, we are at state q means we got a match with P1, P2 up to PQ, right. This is an invariant, you can verify, prove by induction. When I start at 0, I have not done any match, and that is where I am starting. And then once I define this transition function appropriately, you can prove by induction that I maintain this property, that, right. And that is why when I reach here, I have got a match, because I matched with P1, P2 up to PM, and so I got a match, right. Good. So, state number represents this. So, now I get an A. So, delta of q and sigma is equal to q plus 1 if sigma is equal to PQ plus 1, right. The next text is PQ plus 1, because I matched up to this point. Now, the next text comes, if it happens to be PQ plus 1, I just go to Q plus 1. Good. That's an easy case, right. I am here, and if I get any A, then I just go to next state, that is clear. This is only if Q is less than M. What do I do for M? Ooh. Okay, so let us capture that, right. If Q is less than M, because I am here, there is no Q plus 1 state. So, we need to figure out what do I do. But that case is handled with the same thing as if there is a mismatch. So, if I find a mismatch, then where should I go? So, let me define a function to help you with that. Sorry, sigma, okay, sigma, I think that is also, okay, let us call this S function, right. S of t with respect to a pattern P is called a suffix function. Let us define it as is the length. Okay, so is the length of the longest prefix that is a suffix of T. Okay, so you understand what a prefix and suffix is, right? So I give a text, right? For this text, all these are prefix, right? A is a prefix, AB is a prefix, ABA is a prefix, ABAB. So anything starting from the first position and ending somewhere is a prefix. Okay. Similarly, what is suffix? Starting somewhere and ending at the last position is a suffix. Okay. So what I am saying is, suppose let us fix a pattern P. Let us say this is the pattern. Right? This is our P. Now I give you a text. So this is a suffix function, S of so this is my text. What is S of this with respect to this pattern? Okay. So let us read the definition. I am saying it is a length of the longest prefix of P, longest prefix of this, which also happens to be a suffix of that text. So it is 5, right, because ABABA is the longest prefix that also happens to be a suffix of this, right. So this is 5 with respect to the pattern. So it is the length of the longest prefix of my pattern, which happens to be the suffix of the text, right. Now think about it. If I am, so I have matched up to this point, which is I am here, and I had a mismatch, right. So that means I get a new character and I want to know where I should go, right. So where should I go? Well, S of what? This is equal to S of P1, P2, PQ and not quite PQ plus 1. Sigma is the current character, right. I got sigma now. So I want to know where should I go. So I claim it is S of, look at, so I have got matches up to this point, right, PQ, and now there is a sigma which is coming. Now take this string P1, P2, PQ, this sigma, and see what is the longest prefix of the pattern which is a suffix of this, right. So this is what you saw, right, when we never went to. So let us say I am at 3 and I get an A, right. So you are at 3 and get a A. The fourth character is not B, because if it is B I would have gone to fourth state. Fourth character is A. So what I do is now look at I already got matched 3, now I got an A, ABAA, right, and see how much, what is the length of the longest prefix of the pattern which is sitting in the suffix, and that is where I go. In this case the longest prefix of the pattern, this is the pattern which is sitting in the suffix is 1. So I just go from here, I go to position number 1. Okay. So it is essentially S of P1, P2, PQ followed by your new character, and that is where you should go. Length of the longest prefix, which also happens to be the suffix. Okay. Note that it actually handles this case also. Yeah. No, not so. consider this invariant. Remember this is useful. Okay. If I am at state q, I got a match up to pq, right. So, this tells me how many matches you would have done. So, even though you have a mismatch here, but still the length of the longest suffix, which is also a prefix of the pattern, tells me how much match I still have done with this mismatch, and that number actually tells you which state I should be in because of this invariant, because this invariant tells you how much match you got, you are in that state. Okay. And I was saying that note that this handles this also, right, because if sigma happens to be pq plus 1, what is the longest prefix of the pattern which is also a suffix? Q plus 1. So, it goes there as well. So, now that you do not have to worry about q is less than m, because even if q is equal to m, then it depends on your next character, and you look at it and say what is the length of the longest prefix of the pattern, which is a suffix of p1, p2, pm and followed by that character. Okay. So, I am going to now replace this and say this is both is essentially S of P1, P2, PQ followed by this. So, take this text whatever and see what is the length of the longest prefix of the pattern, which is a suffix of that, and that is how much match you would have gotten, and that is the state you want to go there. Okay. So, now how much time does it take to compute this, right, after, because the construction of the DFA is all about computing this transition table for every state, for every symbol. I need to know where I should go, and I need to know where I should go is just basically I need to compute this suffix function, and once I have that, I have the whole transition table, q, sigma, delta, starting state, final state, everything is there. You can run your text in linear time, you can check all the queries you wanted. Okay. Good. So, now what is a naive way to compute this? Right? I mean, you multiply, how many states are there? M plus 1 states, and there is a sigma alphabet. So, multiply by m plus 1 and sigma, capital sigma, times the time to compute this for each one particular sigma. Let us just see how do I compute this very naively. So, what do I want? I have computing so, this maximum this number can be is q plus 1, right. So, I start with q plus 1 because I am looking for the longest prefix of p, that is a suffix of t. So, I start with matching, and it is same. So, I will have p1, p2, pq and pq plus 1. I will check, and if that does not match, then I know that I am looking for q. So, you go and try and match this, and if that does not work, then you just go and slide the window again, and an empty string is always, so this is well defined because empty string is always a prefix of the pattern that is suffix of the text, okay, which means in the worst case you can go to 0, that is what it is. So, so naively I am going to say how much time. You try q plus 1, q minus 1 up to 0, and each one would take order q time, the worst case. So, overall I am going to say just q square. And what is q? Q is at most m. So, that is like an m square times. Okay. So, overall time to compute my machine M where all the work is in computing delta is for each q and a sigma it is order m square. So, there are capital sigma many sigmas and q has m possibilities. So, overall time is order m cube times sigma and for string matching m cube sigma plus n because n to run your text on this. Okay. So, the crux of this is this function, this suffix function, and you need to understand that. Okay. So, at least some improvement. We started off with a naive mn algorithm. This gives you an m cube plus n algorithm, m cube sigma plus n. You can compute the DFA in m sigma time actually, but we will move on because I am going to give you a better algorithm anyway. So, without okay, maybe I should mention this variation of the naive algorithm which is due to Karp and Rabin before I get to. Okay. So, right now we have m cubed sigma plus n and we will improve it to m plus n, okay, and that is the best we can do. But just before that, let us talk about this thing. So, here let us assume the pattern is really small. Okay. So, here is my text. So, I am going to think of my sigma as some numbers, okay, 0, 1, 2 up to some sigma or sigma minus 1. I am going to think of the entire thing as text is a sequence of digits and my pattern is also the sequence of digits, and so which is like this, right. I want to compute and my pattern would look like something like this. Okay. Now, you can think of these as characters, that is the way you usually do in the string matching algorithm, but you can also think of your text as a big number in decimal, right. So, it is 3 into 10 power n minus 1 plus 7 into 10 power n plus blah blah blah. It is a huge number, and similarly this is 2863. Now, so what we will do is somehow if you have an ability to compare numbers easily, then we will just take this number and compare in constant time. Are they same? Okay. They are same, then you got a match. If not, the naive algorithm would now would compare this with this number, right? Okay. Now, can I compute this number 7592 from this number and the text, right? Yes, of course, right? So, I have in constant time, right? What, because you have to think in terms of decimal numbers. So, I have 3759 and I want to compute 7592. So, what do? We will do, do a div or take the coefficient mod, right? Mod 1000, okay, 10 cubed plus 2, right? So, mod 1000 would give me 759, sorry, not plus 2, into 10 plus 2. Okay. So, this is a constant time operation again, right? If you have ability to just compare these big numbers. So, compare these two numbers. So, first compute what this number is, you need to spend some order m time, which is like, right, if you are given this P1, P2, Pm, then you will do P1 into 10 power m minus 1 plus P2 into 10 power m minus 2 plus Pm, and that is this big P, your number, and do the, so this is an order m computation, okay, to compute what this decimal number is, and here is another order m computation on your initial m characters on the text. Take that number and compare them. If they are same, good, you got a match. If they are not, then do this computation, right, into 10 power m minus 1, do mod 10 power m minus 1 into 10 plus the next character. You got a number, compare these two numbers and keep going, right. So, if these numbers are comparable in constant time, then how much time does this take? Order n time, right. There is a order m pre-computation. After that, you are just doing order, basically earlier we had order m into n minus m, but this m has now become constant. So, this goes away, so it is order n minus m time plus the original order m. So, it is order n plus m time, which is as good as you can get, right. So, the only problem with this is that the numbers can be very large, the pattern, if if it is like 500 digit numbers, then this could be million digits, this could be 500 digits. I am expecting that you can compare two 500 digit numbers in constant time is unreasonable, okay. But this still works in practice for all as long as the pattern is small, okay. Now, if these numbers are big, then they had a way around, which is do a modulo some small number and then do your comparison, okay. What would be a problem with that? So, if m is large, what does large mean? It depends on your machine architecture size or whatever. If it is very large, then what you do is you compute P mod used Q several times, but I think probably not. So, do P mod Q for some Q that fits in one word of one machine word, okay. So, now we are all talking about in practice. So, now you do the entire thing in this mod Q arithmetic. So, you take your pattern, compute this big number, do a mod Q, and then do the same thing on the first m characters, do a mod m and then compare. Now, these numbers are comparable in constant times, so which is fine, but what is the problem here? So, they may be same mod q, but originally they may not be the same, but at least one direction it works. If they are different mod q, you know that the numbers are different, okay. At least on that direction you can keep going. The moment if you get a hit which says that these two numbers mod q are different, keep moving. If they are same, then maybe you will go and do your order m match, okay. Whenever you hit the numbers, or if the modulo arithmetic values are same, then you will go and do your hit, and you know you still have your worst case mn time, because you know in the worst case an adversary can make sure that all the mod q values are same, but the numbers are different, and you have to do a mn worst case, but it seems to work. So, worst case, okay. So, let me write what I was saying. Now, p mod q and some alignment of text mod q may match while the actual strings are different. So, do an order m verification then. So, worst case still order mn, but works in okay. So, now you have choices on what kind of queue you would choose. It is like hashing basically, all you are doing is hashing, right. Now, this p mod q is some sort of a hashing you are doing. So, whatever properties you have on hashing, you may want to apply, choose a good queue depending, or if you assume some good distributions, then you may be able to argue that it really gives you a linear time, but otherwise in the worst case mn. But since string matching is so applicable in practice, there are so many practical variations. People have done a lot of implementation. So, there are many things that work very well in practice, which may not have a very good theoretical explanation. Okay. So, now let us get to the classical order n, m plus n matching algorithm due to Knuth, Morris and Pratt. So, this is very similar to the automata based algorithm, but somehow we do not spend order m sigma for computing the automata, but more or less we compute something similar, but in order m time. So, let me just again use an example A, B, B, C. Okay. So, we will come up with something like a suffix function. Let us recall what is a suffix function. So, S of t with respect to a pattern is length of longest prefix of p, that is the suffix of t. Right, and this is what we used when I wanted to compute. If I am in state q and I see a symbol, then you just go to this length of the suffix, which is also longest prefix of the pattern, which is a suffix, that made us compute this automaton. We are going to compute something very similar. So, again the idea is very similar to the automata based algorithm. Given the pattern, we will pre-process it and compute some function like the suffix function, but slightly different. We will spend order m time on that. Then we run our text, and that is going to be an order n time. Okay. So, what is this the prefix kind of a function, right? Okay. So, suppose I have matched, so I am doing this the naive algorithm, and I have matched up to this point, okay, and I have a mismatch here. I have a mismatch. So, in this case you are given this some alphabet, I do not even care about some alpha, I do not even know who mismatched with me, but there is a mismatch. Okay. So, now the naive algorithm says start all over again, right. Then I have my text here. So, if I matched, so that means I matched A, B, A, B, A and something here. The naive algorithm will say start matching from here now, the first algorithm, right. But it does not make, I mean, looking at the pattern, we know that, we know what this character is, right. If I matched up to this point, then from my pattern I know that this character is B. So, there is no point in trying this from the pattern. So, basically you are given the pattern, what can you gain, what kind of knowledge you can gain by saying there is a mismatch somewhere. Okay. So, if I matched up to this point, then I know that this is B because I matched. So, do not try comparing here. In fact, but I know that this is A. So, you could actually directly go and align with this character. You do not even need to compare because you know that. You know this is A because you matched up to this point from your pattern. So, you know here, you know this is B, you know this is A. So, now the next thing you have to compare is this, right. So, this much shift you can do and start comparing from wherever the next character you should be comparing is this. And if there is a mismatch again, you can sort of apply the same idea recursively and say now how much you have to shift and where do I do my next comparison based on whatever I have matched so far, right. So, let me write down and then we will again come up with this kind of a function, right. So, suppose there is a mismatch or there is a match, or okay, I mean we worry about it because there is a mismatch at 6th location. Okay, I am working at this example pattern. Okay. Then next comparison I should do with, I mean, who do I compare? I am going to compare only this character where I have got a mismatch. I want to see how much to, but who should I compare it with? I have to compare it with is with the fourth character of pattern. I am working with this example and whatever I just said, I said if there is a mismatch here, then I know that I matched up to this point, right. So, from the pattern I know what these characters are. So, I know that this is A, this is B and this is A. So, now I just have to compare it with my fourth character, right. Suppose I do mismatch again. So, now I want to understand what is this connection, right. This is the function I want to pre-compute, like the way we did it for automaton. You all said that if you get here, you have to go to this state, and somehow you knew where you are going in some intuitively, and we formalized it, and then we said how to compute it, right. So, suppose I have a mismatch at 4th location, then where should I go, right. What does that mean? That I matched up to this point, So there is a mismatch here. I don't even care about what this character is, and I haven't even gone this much. So there is a mismatch here. So now what should I start? Where do I shift and start comparing, right? I know that this is B, so don't bother comparing your A with this. I know that this is A, which is good. I've got a match. So now which character should I compare now? The second character, right? So somehow if I just, and the knowledge of this requires only the pattern. From the pattern, if I manage to say if I have a mismatch at ith location, then which character of the pattern should I now do my next comparison? Let us call that a sum function, and which I compute, if I pre-compute it and store it, then it tells me a way to just keep shifting and save a lot of comparisons from the naive algorithm. Okay. So, what is this number? If there is a mismatch at 6th location, go to the 4th location. Why 4th location? Let me write down the pattern A, B, A, B, A, C. So, here if there is a mismatch, I am saying what does that mean? That you have got a match of 3 already, that is what it is. So, start comparing with the 4th location, right. What is this 3? P. Yeah, okay, good. So, let us define, yeah, it is again about like a suffix function. So, my pattern P is P1, P2 up to Pm, and for I going from 1 to M, let me define pi of I as, okay, length of longest prefix of the pattern that is the suffix of, so that means pi of I means assume I have matched up to I locations, and I plus first locations I am getting a mismatch. Now, how much do I shift, right? And this is exactly how much of the suffix of, that is a suffix of P1 to Pi. Right? If P1 to Pi, I have matched up to this point. Now, I plus first is a location, there is a mismatch. So, now I am going to do my shift, do my sliding. How much do I slide? Well, if you tell me how much suffix of is still a prefix of the pattern, then that much I can shift. It is very similar to the automata thing, right. Is it clear? There is one little thing. Why is it not always I? The way I have written. I am saying the answer is always I. Pi of I is I. If what I have written is my definition of, because P1, P2, Pi is a prefix of the text, and that is the longest prefix of the text, which is the suffix of this. So, longest, anything other than I, right, something strictly less than I. Give me a prop, because I fails, because I have matched up to this point P1, P2 up to Pi, and then here there is a mismatch. So, now I have to slide it. How much do I slide it? Well, see how much have you already matched. Of course, you matched up to this point, but go, no, this is not enough. Go to a proper prefix, or actually I should put a proper here. Proper, the longest prefix of the pattern, that is a proper suffix, which means that this entire thing is also a suffix. I want to exclude that. I want a proper suffix. It should start somewhere else and end not at 1, somewhere else and end at pi, and see how much I have matched, and that then the next character of that is what I am going to check again. So, let us compute this pi of I for every character and store it. Okay. And then the text string matching is clear, because more or less I run the naive algorithm, start matching, and the moment I have a mismatch, I do not even, so it is like this automata thing, I do not even need to know what the sigma is, what is this character, I do not care. Okay. It immediately tells you that, okay, how much to shift, and then take the next character and compare. If there is still a mismatch, again do your pi computation, whatever you matched, go back and do a shift, keep doing shift. Somewhere your pi I would be 0, you will go shift all the way and start comparing from P1 and you run the algorithm. Okay. How do I compute pi I, and how do using pi I, how do I run my text? I mean, using pi I, how do I run my text? I just told you, but how much time does it take? It requires some non-trivial analysis. Okay. So, let us do it on that example. What is, so if P is AB, AB, AC, A. So, what is pi of 1? Let us compute pi of 1, 2, 3, 4, 5, 6, 7. Pi of 1 is always 0, because I am looking for a proper suffix. So, it has to be empty string. So, pi of 1 is 0. Pi of 2, what is the prefix of the pattern, which is a proper suffix of this, right? Zero again, because I have matched AB. So, I have my I is 2, so I am looking at this, and I am looking for a proper suffix. B is the only proper suffix, right? B is the only proper suffix, and that is not a prefix of the pattern. So, that is 0. Empty string is another proper suffix. So, now I look at ABA. I am looking for a proper suffix. What are the suffixes here? ABA, BA, and A are the 3 suffixes. ABA is not a proper suffix. BA and A are the 2 suffixes. Out of the 2 suffixes, what is a prefix of the pattern, which is A. So, I have 1. So, this tells me that if you are matched up to this point and you got a mismatch here, then you just go, the second character is what you should start checking, that is all it says. Okay. So, if I have gone up to AB, AB, then the proper suffix, which is a prefix, 2, right, because AB is the proper suffix, which is a prefix, and here ABA is a proper suffix, which is a prefix, right? Here 0, because there is no suffix which is a prefix here, and here if you matched up to this point, what is the proper suffix which is a prefix? It is only A. So, once I compute pi, I mean, how do I compute pi? Well, we went through this, but it requires certain computation, and then once you compute pi, you run your text, and so now the string matching should be easy. At least let us write the code for it. So, let us now write KMP matcher. You are given a text and pattern. Text length is n, text this is m, and first compute pi function. We will do this later, how to do and running time of this. Now I am going to run my text on it, right. So, for I going from 1 to n, q is 0, q is whatever I have matched. So, if the next character of the pattern is equal to the next character of I, then I have got one more match. And if q is equal to m, that means I have got a match, right. Q tells me how much I have matched. I start with 0 and the next character of my pattern happens to be the same as the next character of the text. T is running, I is running on the text, then I have got. So, it is like I matched up to this point and then I am waiting. If I match with this, good, I move on, right. If I do not match, we will deal with it. That is where we are going to use the pi function. And if I match the whole thing, then okay. And now Q is going to be so if I do not match, what should I do? So this is fine. If I go and match the next character, I have got one more match, and if Q happens to be m, then good, I found an entire pattern, found pattern starting at position I minus m, and now I am going to apply this pi function and come back here, because that is the proper suffix of P1 to Pm, which is also a prefix. So, that much I have matched. This is very similar to what we were doing in the automaton. The only thing in the automaton is that you needed the next character to do this. Here we just ignored and said, okay, I finished, right. I have got P1 to Pm, I matched all the way. Now, I look at the proper suffix of a pattern, which is still a prefix of the pattern, and say how much I have matched. So, now I start looking for, so that Q tells me how much I have matched now, and then I look for Q plus 1 with the next character. Okay. Now, if I do not have a pattern, while if I did not match, so then Q is going to be pi of Q. Okay, but I am going to say and I is greater than 0. No, Q is greater. Because it is possible that my pi Q, yeah, okay. So, what does this mean? That I have got a mismatch here, that is where it is. The moment I have a mismatch, I apply my pi Q, which tells me how much I have matched now, suffix, and then I take the next character, which is Q plus 1, and compare it with I. If I got a match, great, I will say, okay, I have got one more match. But remember, this Q is now different. It is a smaller Q because this while loop has moved it back to pi of Q, right. So, now I got a match and I will keep going, but if I still have a mismatch, then I apply pi function again. right? It does another shift and then I compare it with it, keep doing this, right? Until Q becomes 0 or you got a match. If Q got a 0, then I just go to the next character and start matching here again. And if this Q plus 1 also did not match, then I have to just move my I and compare it with this character, and that is what will happen, right. If finally suppose Q became 0, you got out of the loop, you check the next character with, which is the first character because Q is 0, check the first character with the next location. If they are same, you got a one match and you move on. If they are different, then you get out of this and I gets changed. Now I give up, right. This character does not match with anything, any of my prefix. So now I just move on to the next character and start matching. Okay, so that's what, because I will move, because this is the entire code. Okay. So we'll worry about how to compute pi later, but here is my algorithm. Okay. Now it's order n, but it's not quite obvious why it's order n, right? Because of so much happening here. When I have a mismatch, pi is already computed and stored there, but I at this point so many characters are being compared with this character. That's a problem. With this character, I compare somewhere and there is a mismatch, somebody else is a mismatch, and then I move on, right. So what is the overall running time? But this is the entire algorithm, right, because as long as I am matching with my text, it just executes this and I keep moving. I changes, Q changes, then I keep moving. The moment I have a mismatch, then I do my shift using the pi function. I got a Q, and then I take the next character and compare it with Y. And if it matches, fine. If it doesn't mismatch, and I just keep pushing Q back and comparing with this I, and runs this algorithm. Okay. So the correctness of the algorithm should be obvious. I mean, Karman book has, like, as usual, about 3 pages of correctness. You can go through the formal proof, but from the definition of pi and exactly what we were doing, the correctness should be obvious. Okay, one can again prove inductively various invariants, and you can prove correctness. Now the running time, why is it order n? Considering the fact that when there is a mismatch, I mean, basically because there is this while loop, and if it's just a for loop, this is a constant time computation, this is a constant time computation, all they are great. The only problem is there is this huge while loop happening, and it can happen several times, right. This is a very nice amortization argument here to tell you that it's a actually amortized complexity of one execution of this for loop is constant. Okay. And the way to think about it, okay. So pay attention to Q. Okay. Okay, I still have to talk about how to compute this and argue the correctness. We'll do that next time. But let me just complete the order n running time for this algorithm. See, actually, how to compute pi is going to be very similar. You're going to pretty much run the same algorithm. Instead of the pattern and text, you have the pattern and the pattern. Okay. Otherwise, it's pretty much the same kind of argument, same analysis, but we'll go through it just as a repeat of understanding this. Okay, why is this order n? Look at Q, the variable Q. What are its properties, right? Q is always greater than or equal to 0. It never becomes negative, right? Q is always, because I start with 0 and I keep applying this only when Q is greater than 0. The moment Q becomes 0, I get out of this and move my I. So Q never becomes negative. How many times Q gets increased in one step of the for loop, right? Q starts at 0 and has at most n increases, right, and is increased and it gets increased only here, and that happens only once in each step of the for loop. In fact, you may not even get here at all, right? You might just go here, and get out of it as well. So, at most q gets increased. So, q starts at 0 and gets pushed at most n times, and when it increases only by 1, right. So, increased by 1 at most n times. Okay. So, the overall time for this steps as order n is clear, right. This is constant, there are n steps it's happening. So, this is overall n. So, I want to argue that overall the total time for the while loop is also order n. That is all I want to argue. Okay. Why is that? Because at every execution of the while loop, q gets decreased, strictly decreased, because it's a, I erased the pi function, it is the proper suffix and so on, right. So, q gets strictly decreased, but can it get, given these two conditions, you can't decrease it by much, right. Q is slowly going up, it can go only up to n. So, take any number, it just goes up to n, and this while loop is pulling it down, right. And at every execution of the while loop, q gets strictly decreased. So, it must be obvious from these two statements that this cannot be more than order n. Okay. Is there a nice clean way of seeing this? So, this, right, all of this imply that total number of execution while step is order n. So, so one way you can think of this following charging argument, right. Every time when I increase q, I account 1 and put one other charge for the while loop when it brings it down. So, you do not need to pay for it, and or put a charge of that number. Okay, I do not know, you should think of a clean way of arguing this. I claim that it just follows from these 3 steps that okay, I will think of a very simple amortized way of proving this overall. So, this step takes constant time, and here I am going to say overall the executions in the for loop, this is order n because of these two conditions. Okay, I think I will stop here. So, next time we will again prove this formally, talk about pi function, talk about the running time for it, and we will argue that that is an order m function, and so it is order m plus n.